Let's talk a little bit more about the logic of hypothesis testing. The quote you see up here is from a statistician, C.A.B. Smith, in 1960, who's criticizing hypothesis testing, or rather the way it's usually done. He was pointing out that an awful lot of hypotheses are fairly silly because they're logically almost impossible. So, yeah, it's something to keep in mind. Not everybody really likes the hypothesis testing system. Some people love it. Let's move on and see what we can learn about it. You need to understand it whether you love it or not, and I hope you form strong opinions about it, and I hope those opinions shift around and change a bunch of times as you learn more about it. Most people form strong opinions, and then if they learn more about stats, those opinions change and then change again about hypothesis testing. It's a divisive, contentious subject. My opinion currently is it's extremely useful, but it's overused. Actually, this is a common opinion. I'm being pretty trendy by having this opinion. A lot of people think this. For this video, let's understand the two-hypothesis system, understand the logic of the adversarial hypothesis situation that it involves, the benefits of an adversarial hypothesis situation for research, because there are clear benefits, and describe the general nature of the null hypothesis. So, scientific method in the junior high version is just scientists observing things and then understanding the way the world works. And I would suggest that this is still an important part of science, and in past decades and centuries it was a dominant way that scientists did things. It's not quite enough all the time anymore. For instance, Galileo Galilei rolled some balls down some angled piece of wood to determine the force of gravitational acceleration, and baby Albert became scared of fluffy things when John Watson banged a loud bangy thing behind a poor little boy's head when he was petting a fluffy rabbit, and Philip Zimbardo turned college students into power-tripping prison guards and cowering rebellious prisoners and stuff like that with a simple experiment in the 1970s. So all of these things happened, and they might seem like they're fairly obvious, but you should be very skeptical of the term obvious. Nothing is obvious. And if something seems obvious, sometimes we really need to study it and find out if it is. Sometimes it is, sometimes it isn't. But our own sense of something being obvious is something we should not trust very much, because psychology has taught us that we're not great at understanding what's obvious and what's not. So Galileo had this kind of problem that maybe he didn't recognize as much as later generations did. How fast should the balls roll? How much should they accelerate? And there's variability. He rolled the balls several times, and he came up with slightly different answers every time. And he just kind of averaged them out, as I understand it, if I remember correctly, and said, the average is probably the force of acceleration, but there's more to it than that. Why would that average be what the true force of acceleration is? Should that have been happening? Should it have not? Baby Albert became scared of fluffy things. Well, would he have become scared of fluffy things anyway? So it was an N of 1, a sample size of 1. How did John Watson know that it was him banging the gong behind poor little Albert's head? It was actually this big piece of steel that he whacked with a mallet or something. It was really terrifying for a little boy. How did Watson know that baby Albert was going to respond this way? And how does he know what would have happened if he hadn't done this? Maybe baby Albert would have become scared of rabbits anyway. And how does Zimbardo determine that the college students, that the change or the apparent change in their behavior was more than what would have happened just if he'd left them alone, if they hadn't been living in the dorm wing and dressed up like police guards and stuff like this? So we need something to compare against. You can't observe the world all the time. Sometimes you can, when you observe the world, you need to compare it against some benchmark to know how much of a thing you're looking at, and how much you should be. People are really bad at factoring in information, especially unseen information, into our judgments. We're bad at putting together math and numbers in our head in general. And then when some of those things are not right in front of our face, we're even worse. So it gets really difficult sometimes. We forget about what might have happened in other circumstances. We fail to consider the normal state of things, the baseline, like what is happening. We fail to accurately consider that. Sometimes we think we consider it, but sometimes we're not very accurate in thinking of what the baseline, what the regular business as usual situation is. These and other things lead to biases. A bias is being systematically wrong. A bias isn't being all crazy, random, all over the place wrong. It's being systematically wrong. So there's a hindsight bias where we tend to believe that we understand what happened just because it's already happened, or that it has to have happened. There's confirmation bias where we convince ourselves that what we see agrees with our previous preconceived ideas because we only look for or only value certain kinds of information while we're out hunting for the information we want. There are an awful lot of very good people, normal people, who believe things that don't actually fit the evidence because our brains are kind of primed to find the wrong thing in certain circumstances. Most of the time, our brains are great at finding a pretty reasonable view of the world, but in certain circumstances, our brains screw up. For instance, eyewitnesses are not very reliable, but people believe that they are. Rhinoceros horn does not cure cancer, but people all over Asia believe that it does. A lot of people believe that crime has risen steadily since the 1960s, which is completely false. It rose kind of up until the early 80s, and then it's been dropping ever since then. Statistically, you're safer on the streets of America on average right now than you were in 1960. Our justice system kind of gets this, which is why we have this adversarial system in court. You can't just go in and have somebody accuse you of all the stuff that you've done. You have to have somebody to defend you also. You have to have somebody to bring up all the stuff that people would not think of normally. You need to have some people bring up the possibilities that the jury and the judge have not thought of yet. So this was an important part of the whole system. And now theories are a big part of how we regulate ourselves in science. We don't just go out and observe the world. As it turns out, we could get into the details, not right now, but there are lots of problems with just observing the world and finding out what's going on with it. You can get to a certain point with that, but then your biases can sometimes take over and do crazy stuff. A theory is one thing that helps keep us honest and helps science progress. Some people think that theories are the key element of science that makes progress possible. And theories tell us what to look for and how much of it to look for. A good theory has some numbers in it, some real specific numbers. Scientific observation is almost always guided by these theories. And so we observe things and then we find out whether our observations fit our theory, or whether they fit well or not so well. It's a range of possible fitting of the theory there. And then if the theory is correct, we have to say to ourselves, if this theory was correct, would it have produced these results? The problem is it's almost never perfectly clear-cut. The results almost never perfectly match the theory, so we have to decide how close of a match should it be. The speed of light, according to my theory, should be 300,000 meters per second squared, but I got 296,000 meters per second squared. So is the theory about the speed of light wrong? Or was there something else going on? Was it like a bad day? Did my instrumentation glitch a little bit? We always have to ask ourselves these questions. We're never free of these questions. Well, theories are very generalized, sometimes very complex sets of propositions, sets of statements about the way the universe works. And to test them, we can only usually test a piece of them at a time in a specific situation at one time. And so we have to make a hypothesis. A hypothesis is like a little mini theory that's just for one particular research situation. A hypothesis is an extremely specific prediction about what should happen in a particular situation if a theory is correct. So some examples. If general relativity is correct, then we should see some stars that are directly behind the sun during an eclipse. We should see them as if they weren't behind the sun because the light will bend around the sun, and to us it will look like the stars are to the side of the sun, when in fact we know from astronomical observations that they're directly behind the sun. If the culture of honor theory is correct, and that's a fun culture or a fun theory, you should read up on it, then men from the US South should be more prone to violence if you threaten their reputation. If the serotonin theory of depression is correct, and a lot of people think it's not, there's more and more evidence that it's not, then getting more serotonin active in depressed people's brains should ameliorate the symptoms of depression. So those are hypotheses. If this theory is correct, then in this particular situation, this is what we should see happen. But a hypothesis alone can't solve the problem that real-world data basically never perfectly fit any prediction. So you do the serotonin theory, and you test that, and you increase serotonin in a bunch of depressed people's brains, and 76% of them report reduction in symptoms. Is that enough? Should it have been 100? Would 50% be okay? How do you know? How do you know how much is enough? Any given theory is probably not 100% correct. It's almost impossible to think that any given theory is 100% correct at any given time, because something better is going to come along and show us that the previous one had problems. No measurement system is 100% accurate or precise, especially in psychology, where we're using some really odd things to measure sometimes. Well, cognitive and neuroscience, they do a little better, more precise with their measurement, but personality, clinical, counseling, social, a lot of our measurement systems have a lot of noise or random variability in them. There's always a mismatch, therefore, between our predictions from our theories and the actual research results. Always a mismatch. So how much mismatch is okay? And this is where hypothesis testing helps us. And there are other ways to do this too. There are other inferential statistical procedures like confidence intervals and parameter estimation that help us tackle this. But hypothesis testing is the most common. So we use hypothesis tests to figure out how plausible it is that this level of fit between our data and our theory should have happened if our theory is correct. So if our theory is correct, then how likely is it that this data or more extreme should have happened? So one way we do this with the hypothesis testing system is we create two hypotheses that are directly opposed to each other. One hypothesis in many cases covers one set of possibilities, and then the other hypothesis covers all other possibilities that might occur. So we formulate an adversary hypothesis. We already have one hypothesis in place that we love. It's our hypothesis. But we formulate a different one that is directly opposed to it. So if our hypothesis is wrong, then this other hypothesis is right most of the time. Sometimes there's a third possibility, but usually we make it so that either one or the other must be right. And if one is right, then the other one's wrong. So they're mutually exclusive and they cover all possibilities. So sometimes this adversary hypothesis is a devil's advocate position. Let me just play devil's advocate here. You think that this is caused by such and such, but couldn't it in fact be so and so? Or sometimes it's conventional wisdom. You could say, you're trying to prove that culture of honor, blah, blah, blah. Well, the conventional wisdom would suggest that what will actually happen is there will be no difference. So the best case scenario for your results would be that the results will clearly favor either this new hypothesis, the devil's advocate adversary hypothesis, the null hypothesis, or your results will clearly be more consistent with the original hypothesis, the one that you probably actually are leaning towards yourself because you're a scientist and you thought of it over many, many years. But in reality, realistically, it doesn't always happen that way. So we run the study and we collect the data. We check the fit of the data to each hypothesis. In other words, we check the data and we evaluate it and say, how likely is it that these data could have happened if this first hypothesis is actually what's going on, the truth. Now let's go back and say, look at the same data. How likely is it that this data might have happened if the second hypothesis is what was really going on? We retain the hypothesis that has the best fit and we reject the other one. Retaining a hypothesis means we say, okay, it's plausible. I'm not saying it's true, but at least for now it seems believable. And rejecting says, well, right now, this is not the best solution. We don't ever say true. We don't ever say false. We don't prove a hypothesis. Just don't ever use the word prove. Don't ever use the word true when you're talking about the results of a study. Hypothetically, theoretically, in theoretical la-la land, a theory or hypothesis might be true. But we will never know. And so the results of our studies are not about truth and falseness and proving or disproving. We don't do that. Well, sometimes disproving. Instead, we support a hypothesis. The data support one hypothesis or they fail to support it. We reject or retain the hypothesis. This is not the same as true and false. So moving on, the null hypothesis, H0, is that adversary hypothesis. It's that devil's advocate or conventional wisdom hypothesis. People say H0 or H0. Not N-O-T, but N-A-U-G-H-T. H0. Not means zero. So you can say ho if you want. We use a default version of the null hypothesis in most cases, which is that nothing interesting is happening. So our theories are usually that there's something interesting. And so the null hypothesis is that no, there's not. for instance, if we're comparing two groups and our theory says this group should have higher IQ or something than this other group, the null hypothesis says, nah, there won't be any difference. It doesn't usually say the reverse will be true, like, group 2 will actually be higher than group 1. No, it usually just is nothing. There will be no difference. If we're testing a clinical intervention and we think this clinical intervention will radically reduce the symptoms of anxiety disorders, well, the null hypothesis will be, no, it won't. We might say that we are, introducing special sugar water to these rats that will increase the time that they spend, in social behavior. Well, the null hypothesis might say, no, it won't. It won't increase anything. They'll just continue at the baseline. So we call our preferred hypothesis the alternative hypothesis. That's just the term for it. And the null hypothesis is that devil's advocate type hypothesis. Our preferred hypothesis is usually HA or H1, but sometimes we give it fancy names like H theory X, H Johnson theory, H3, H standard, etc. So there's Gregory Peck. Could rocket suit better than anybody. Classic null versus alternative hypothesis is a court trial, or one classic analogy. The prosecution has a theory. So let's say that the alternative hypothesis is that the suspect is guilty. The prosecution is the scientist in this case. The prosecution is saying, you are guilty of causing human behavior to do something. But the alternative hypothesis is that the suspect is guilty. Something is going on. There is something to find here, something to see, something to be interested in. Something happened. The defense has a different theory. Let me present to you a different theory. And you've probably seen this on CSI and Criminal Minds and stuff like that. They even use that phrase, let me present to you a different theory. Let me suggest a different theory. The different theory, the suspect's not guilty. Nothing happened. In fact, everything you see is a result of totally understandable things happening. So, yeah, there's no reason to think that there's any guilt. The null hypothesis is the default. The defense has the default, innocent until proven guilty. The burden of proof is on the alternative hypothesis. So you have to find evidence to support the alternative hypothesis, and if you don't find enough evidence, it's not like a draw or whatever, it's that the null hypothesis wins for now. The null hypothesis is what you retain for this particular study, unless you can find enough evidence to support the alternative hypothesis. And this has to be the case because it's basically impossible to support or prove a negative. Yeah. Anyway, another advantage of using the null hypothesis is that pure observation is even logically problematic. We don't know what the specific reality even looks like, because we only know that from our observations. And so if we're trying to prove something about our observations, we're going in circles. How do we know what the results are even telling us from imperfect measurements and possible biases? The null hypothesis at least provides a known model for comparison. So if we're studying some new area and we don't know what to look for, we can specify a null hypothesis that pretty much everybody can agree is what we might see if there's just nothing going on. We don't know exactly what is going on, but at least we can start by seeing if it's the same as nothing. Nothing is usually easy to specify. You can logically specify a nothing hypothesis even if you don't really know much about what you're studying. And so that's where a lot of people start in early stages of research. We know exactly what it is. We can specify its characteristics. Its characteristics are nothing is happening, the mean is 0, stuff like that. We humans need some kind of structure to seriously consider what things look like if our pet theories aren't true, because we're too good at imagining the world according to what we want to be true, and we forget the possibilities that it's not. I mean, most people have had this situation where you get disappointed and your hopes shattered, and you realize that whatever it was you were hoping for, you weren't even thinking of the possibility that it might not happen the way you wanted it to. And when it doesn't happen the way you wanted it to, you realize, oh crap, I didn't even consider the possibility that this wouldn't work out. Well, that happens in all sorts of domains, including in science. So let's look at some examples. So in a drug study, subjects with an illness receive either the real drug or the placebo. The null hypothesis, no difference in symptom change between the drug and the placebo groups. The alternative hypothesis, yes, there is a difference, and probably the difference goes this way. The drug group will have more improvement in symptoms than the placebo group did. In a psychotherapy study, let's say standard therapy versus a new model, the null hypothesis, no difference in the effectiveness of the two methods, or no difference in symptom reduction, very similar to the drug study. The alternative hypothesis, the new method is more effective or produces greater positive symptom change than the standard method. Current temperature fluctuations globally versus fluctuations over the past 1,000 years. Now we're getting kind of weird, but it doesn't matter. Temperature fluctuations, all you have to do is like compartmentalize that and say it's a thing. It's going to be a number. It's going to be high or low. That's all we need to worry about for right now. The null hypothesis is that the current fluctuations are no different from how they've been for 1,000 years. The alternative hypothesis would be that current fluctuations are more intense than the past 1,000 years. The null hypothesis is no difference. The alternative hypothesis specifies a particular difference. Predicting an association between competition for resources and ethnic violence. Actually, this is a robust study. The more two ethnicities are in competition for resources like food or water or money or something like that, the more likely they are to be violent toward each other. The null hypothesis would be that resource competition is not associated with ethnic violence. The alternative is it is associated and positively associated. So we have up here a hypothesis about the difference between two groups, another hypothesis about the difference between two groups. Here the hypothesis about one group of observations from now compared to, observations from back in the day. And here a hypothesis about an association between two separate variables. For hypothesis tests about everything you can imagine, anything you can do to describe a data set, there's a hypothesis test for that. So summing up a bit, there are two hypotheses. We do the data collection, and then we don't really guess. We compare our data to each of those predictions, and we determine which prediction is more consistent with the data, or which prediction the data are more consistent with. Another way of thinking of that is we're looking at our data and trying to determine which theory most likely produced them. So which world, the world of the alternative hypothesis, that theory, or the world of the null hypothesis, that theory. And then we make a decision about the hypothesis. We reject the null and therefore retain the alternative, or we do the opposite. And that's it for this little lecture. We'll move on to other lectures. Next time, we're still going to keep reviewing null hypothesis and alternative hypothesis testing concepts.